Well, hello, and welcome to class 15. All right, today we're going to look at inter-process communication again, but this time for something that's more appropriate for distributed systems. We're going to look at a couple of options for doing that. So the first one, before we get into that though, is we looked at a variety of ways to get processes to communicate. We looked at queue objects, we looked at pipes, we looked at value and array objects, manager objects. We even looked at shared memory blocks that can be accessed by both processes at the same time. And each of those has some advantages and disadvantages. But one of the things that they all have in common is this shortcoming that the processes have to be on the same operating system, on the same machine. And that makes all of those objects unsuitable for a distributed computer system or a cluster-based, cloud-based parallel computing system. So for example, if we have a queue, we have a process, another process, they have to be on the same machine. You have a pipe, you have a process and a process, they have to be on the same machine. So what we're going to look at today is getting around that restriction and finding something that does work for that. So to achieve that, we're going to need a different method to do that. So there's several options that are available. We're going to look at some of those today. One is to use kind of standard methods that have been around for a long time, and that's like, for example, sockets. Sockets are kind of how the internet works. When you have a web browser and you type in a URL and it loads a page and you get that, that's communicating with your client process, the web browser, communicating with the web server process, and sending a request, getting a response, rendering that on the screen. So that is a form of inter-process communication. It's processes communicating with each other where they live on different machines. The cool thing about sockets is they could also be on the same machine. You could have a local process, another local process, and still communicate with those with sockets. And then there's another thing that's kind of an abstraction layer that's built on top of sockets. It makes some things easier, and that's this multiprocessing.connection. Where we can make a multiprocessing.connection object and use that. But behind the scenes, that just uses sockets. It just abstracts and simplifies some stuff for us. All right. There are also some libraries that I would encourage you to take a look at if you're doing a large project. There's MPI, which is kind of a standard for the message passing interface library. It's been around a long time. It's kind of a standard interface to have a process on one machine communicate with another one for distributed systems. And there's a lot of stuff that can do, but there's some other ones as well that I'm going to mention here. There's this Pyro4, which is a Python remote object library that allows remote invocation of object methods, or you could think of them as functions. And there's also this thing called Array, which is a powerful module for remote and distributed applications specific to Python. MPI is not specific to Python exactly. This is a Python implementation of a standard message passing interface. So you could have that work in C, C++, C#, all kinds of other languages, but there is a Python implementation of that. And then Pyro and Ray are a little more Python specific, but if you're writing a large distributed application, you might take a look at these because they have a lot of things to offer. But we're going to focus today on sockets and multiprocessing connection objects. All right, so let's talk about sockets a little bit. So with sockets, they're probably they're definitively the most widely used network communication methodologies. The entire internet is based on that. So underlying protocols such as TCP and UDP or TCP/IP, both IPv4 and IPv6 are sockets, use sockets. Also Unix UDS, CAN, packet, etc. are all supported by the sockets interface. So sockets itself is kind of an API or programming interface that supports multiple underlying protocol methodologies. And sockets is also nicely positioned because it can support both stream-based and datagram-based communication. And if you're in the networking and communications class, we're going to spend a lot of time looking at how sockets work at a lower level as well. And if you've already taken that class, you've already seen that. But here we're going to be using it to talk between processes. So web browsers, web servers are built on sockets programming. And the internet, since it's largely built on TCP/IP, we're going to discuss how sockets can work to communicate data across some streamed connection from one place on the internet to another place on the internet. And by nature, that has to be inter-process communication. All right, so let's dig into the programming a little bit. The first thing, this is pretty easy to do in Python. So the first thing we need to do is create a socket. So what is a socket? A socket is like a connection to the networking subsystem that we talk to that networking subsystem through. So before we do anything else with that networking subsystem, we have to create a socket. We have to create one of those connections. You can think of it as like this is plugging a phone into a jack on the wall or something like that in software. We're creating a place to plug into to do something. So the first thing we want to do when we create that socket is you just call import socket, socket.socket, and socket.af_inet is the address family for internet. And then socket.sock_stream means that we wanted a streamed connection or a connection-based thing, not a datagram based. We want something that's opened, and then you can just feed data in one end, it comes out the other. A lot like a pipe, but it's a pipe that exists from one machine on one end of the connection to another one on the other end. Now there's also sock_dgram, which sends things as individual packets rather than a stream that's like a pipe. So the two parameters specify the address family and they specify the connection type. And here we're going to use socket with internet or IP addressing and a TCP stream, sock_stream there, meaning it's you open the connection, you can feed data in, when you're done you close it. Very much like a pipe, but a pipe where the two ends can be on different machines. So once the socket has been opened, we can use it to connect to another process on another, either on the same machine or on the other machine. So to do that, we would need to specify the two things to connect, so s.connect. And this is all from the client point of view. So from the client point of view, we would connect to some machine at some port. And the port number, you can think of that like the extension number. So that means one machine can have multiple programs running using different ports. So port number is a way to sort out which program we're talking to on the other end. And HTTP is usually on port 80. HTTPS is the secure version that's on a different port. There's different ports for different uses. And when we were writing our server code, the kind of listening side that's going to listen for incoming connections, we'll look at how to do that in a second, then you would specify what port you want to listen on. In other words, this is the port I'm going to listen on, and then the person connecting needs to connect to your machine and that port. And this doesn't have to be the host name like this. This could actually be just an address. So you could put, for example, 146.85.1.1 or whatever. You could put the actual IP address there rather than the domain name. If you put the domain name, it'll look it up and get the address and put the address in there for you. Okay, for that to work, we need to have a machine on the other end, a process on the other end, be listening for that address and that port, on that address for that particular port. So the listening machine is usually called the server, and the connecting machine is referred to as a client. So the server code is going to be a little more complex than what we had back here. Notice this is just a few lines of code. We create a socket, and then we connect to that socket. So on the server side, we're still going to create a socket. It still has the same address family, same stream. So the socket gets created the same way, but there's another couple steps here. We have to bind that socket to a port number, and we do, in this case, socket.getHostByName. That's getting our host name, and that's the port number that we're going to listen on. So we're going to say listen on my host name for that port number for incoming connections. And then the last thing I have to do after I've bound that port to this is I have to say, now listen. And this number in the parentheses there, that's what's called the backlog. That's how many, we don't have to worry too much about that, right? But that's how many pending incoming connections there can be before they start getting rejected. Okay, so after we have that, on the server side, we would enter a loop that's going to accept an incoming connection as it comes in. And when the incoming connection comes in, we get this tuple filled in with a return from that gives us the socket that the connection now is on that came in. And then we have the client address, which is a little address thing that says who it is that connected to us. What's their address? But what's interesting here is the server socket here. This is the listening socket down here. This is the client socket. This is the one that we communicate on. And the reason why those are different is when a connection is accepted, it creates a duplicate of the listening socket that has all the same things for us to talk on. So this one can continue listening for other connections that are coming in. So after that, we want to do something with that. So we could send data or receive data. So just like with a pipe, we have send and receive. We could receive a request, send a response, or they connect and we just send them data and they send something back to us. And once we're done with that conversation on this client socket, we would close it. Okay, so one thing to note here is that for this to work, one machine has to be listening. That's the server that we just looked at the code for over there. Notice here are the steps for that server. Create the socket, you bind, you listen, and then a connection gets accepted. That blocks until a connection comes in. Once a connection comes in, we read and write. And when we're done, we close that socket. Now on the client end, when we connect, we don't have to bind, we don't have to listen. We just do a socket, we make a connection with connect, and then we write, we read however many times we want to or need to, and then we close it when we're done. So the following page, there's going to be a client and server example. So you could actually write this code and try it. But you'll notice here, import socket, there's the socket object that gets created. I do mySocket.connect. And here I'm putting 127.0.0.1. That's what's called the local host. That means that's a special IP address that's assigned to your local machine. And here I put in the port number. I just put hex 1234. You could put whatever port number you want as long as it's not being used by another listening process or another socket at that point. And then here I do data mySocket.receive. I say receive up to 2048 bytes. And then when I receive that data, I decode that in Latin and print it out. And this decode is because it comes in as a byte string or a byte array, not a string. This converts it into an actual string. And the Latin there means it's an ASCII. So that's the Python 3's way of encoding ASCII strings. If you're using Python 2, you wouldn't have to do this .decode. Now on the server side, it creates a socket, it binds to that socket, it listens on that socket with a backlog of 5, and then it enters this loop where it waits. When a connection comes in, we accept it. We then send the message hello, we encode it in Latin, encode it as a string. When this receives it, it decodes as that string. And then we close that client socket when we're done. Now notice here we're stuck in an infinite loop that will go on forever. So we'll never get down here, but we'll go back and receive another connection, accept another connection, send hello, close, accept another one, send hello, close. This is like a server that just serves the string hello. A little bit of a trivial example. But notice we have all the code we need to have both the client make a connection and receive that hello, print it out on the screen, and then exit, and this one just sets up to serve hello over and over again to whoever connects to it on that socket. All right, a few notes and details. Send and receive work on data streams. So in other words, just like with a pipe. Send, sends things, pushes things into that pipe. Receive, pulls things out of the pipe. And like pipes in Python, sockets are duplex by default. In other words, you can send and receive on one socket that's been opened. So think of that socket like a connection between your process on the server and your process on the client. And once the socket has been created and the connection has been accepted, they can each put data in and talk back and forth. One thing to note though is that send will return the number of bytes that have been successfully sent. So if you have a very large message and you say to send it, it might send just the beginning of it, but it'll tell you I sent this many bytes. So that means it's up to you, the programmer, to then say if send did not send all the bytes that were available, then call it again, but with the next block of data. And if it did send all that, call it again. And it's also important to note is that when the socket.receive returns a block of data, it might not be all of the data that was sent from a given send. It might be a smaller amount that comes through. So it's kind of like a stream, but you can't really control the timing. So if I say send and it says it succeeded with that number of bytes, we know it got to the other end. But on the other end, when it receives a block, we don't know if that's all of them or not. So that creates a little bit of complexity for us. So that means that TCP, it does guarantee the reliability of the transfer. In other words, when send says that it sent data, we know it was successfully received. Or when receive returns a number of bytes that it said it received, we know that's guaranteed to be the actual thing that was sent. It has checks in there for checksums and packet sequencing, and missing packets will get re-requested automatically. It transparently does all that for us. All right, a few final details about sockets here. And this was a pretty quick coverage of that. And we're going to have a lab where you get to play with this later, but also in the networking class, you're going to be playing with this. But note that the server creates a new socket to talk to the connecting client. That leaves the original one there, like I mentioned earlier, to accept other incoming connections. So it's common to spawn a thread. This is the concurrency class, so it's common to spawn a thread to handle each active socket connection, so the server is free to handle other incoming connections. And one way to think about that, or like to think about that, is like think about the listening socket, the one's listening for incoming connections, like a receptionist. It comes in and the phone rings, they answer it, they immediately transfer it to a representative to handle that call. So you don't have a web server getting a busy signal, and that's what that backlog we saw of 5 was earlier. That's how many can be pending before it starts rejecting those other connections as I'm too busy to handle that right now, before they get a busy signal. So how do we spawn those threads? Well, we do that in the main loop. We accept the connection, and then we create a thread and pass the client socket and client address to that. And then now that thread that we've just started will handle that until it's done. And when it's done, that thread would then close that socket before exiting. And that frees this up to go back up and accept another one, spawn a thread, go back up, accept another one. So this one can be accepting connections while other ones are being handled. All right, now, dealing with stream data, send and receive only deal with streams of byte data. Meaning that if we want to send more complicated binary data or something that's structured in some way, like data for our game server that has the player code and the world code, or maybe you want to send something like a texture image to update something in the game, then we have to have a way to encode that. So that means that if we want to send arbitrary data across that socket, we have to encode that data in some way. So to encode program data to be sent across the stream, we have to serialize that. And there are a number of options for that, for serializing the data. In other words, if you have an array of like bullets, and you want that to be in your game server and show up on every player's screen, you want to see all the bullets flying around, and you want them to look the same, you have to have a way of sending that data. So we need to encode that in a way so when they receive that block of binary data, bytes, it converts it back into bullets in some way. So the options we have, binary, JSON, pickle, XML, these are all ways of serializing data. And then there's another one that I've actually used before in some commercial things that I've worked on for, and also for network games, called Message Pack. And that's a very fast cross-platform multi-language library. So it's not, it's a little more compact than JSON. It's a little more cross-platform than just raw binary. And it's not Python specific like Pickle, and it's way less overhead than XML. And so for something that has to be fast and compact, I just suggest looking at Message Pack. And you could also do it yourself. You could use Python's pack and unpack feature if you wanted to, which is sort of what this byte arrays up here would do with pack and unpack. But you could write your own serialization system if you wanted to. And actually, if you're in the networking class, we'll see message pack in there toward the end of the semester. Okay, so a couple things here. That I want to quickly mention, and that is the JSON and Pickle and Message Pack all have some commonalities that they also I could put XML in that as well. And really, what I would suggest is taking a close look at what those have to offer. The nice thing about Pickle, it's a standard thing in Python. Nice thing about JSON is it came from JavaScript, but almost every programming language supports it in some way or another. It does not, however, support Python objects directly. And then we have Message Pack, which is also this cross-platform multi-language serialization library, similar to JSON, but much more performant if you absolutely have to have a small amount of data and high performance with packing and unpacking that. Now, all of those support the same kinds of methods. So you really, whether you use one or the other, they kind of work the same way. It's just the underlying representation is different. So they use this dumps, which stands for dump string, which is a method that takes an object in the parentheses and it converts it into a serialized byte string version of that. And then loads, which does the opposite of that. It takes that serialized version and it turns it back into that object. And that works for with all three of those for most basic data types, as well as containers like lists and dictionaries. So you could use any of these. You could take a list of tuples for bullet positions and do, for example, JSON.dumps, pass that bullet list of tuples into that, and it will serialize that. And then on the other end, you can say deserialize that, put it into this list, and now you have that list on the other end. All right, so essentially, looking at how that would work with each of those, here's some object we have. JSON.dumps, pickle.dumps, messagepack.dumps, they all work the same way. That gives you the serialized data. And then to deserialize it, JSON.loads, and actually this should say pickle.loads. Let me fix that. Or messagepack.loads. So those all work the same way. So note that there are some restrictions with these, but in general it allows us to pass objects from one process, put it into a socket, on the other process pull it back out, and then the object pops out on the other end. So it allows us to create this kind of interface where you, rather than just thinking of it as feeding a stream of data, of bytes into the object or into the socket, you can think of it as like, I'm going to stick an object in this end, and that object's going to pop out the other end. Okay, now, so the overall process looks like this. Here's the sender. They have an object they want to send to the receiver. They serialize it. They send that serialized version over socket.send. That goes into the cloud of the internet and pops out the other end. The stream pops out over here. And then we deserialize it on the receiver, and now we have the object in our receiving program. So note that the sender and receiver can be anywhere. They could be on the same machine. They could be on the same LAN. Or they could be on completely different parts of the internet. So it could be on the other side of the world. You can talk to another process like that. So also note that there are some details missing up there. Again, with send, it will return the number of bytes it sent, but might not be the size of the entire object. So we need to have a loop that makes sure to resend stuff if it didn't complete. And on the receiving end, we need to make sure that we received the entire object before we try to deserialize it. So it's also important to understand that additional processing adds some overhead, that the serialization, deserialization, there's some overhead associated with that. And let's take a quick look at some of the other simpler approach that abstracts some of that for us, and that's this connection object. And that's part of the multiprocessing module itself. So that offers a slightly easier way to send and receive objects with this multiprocessing dot connection. And what that does is that uses behind the scenes, it uses pickle, which is Python's built-in way of doing that. And so anything that can be pickled can be sent across a connection object. And so you can think of it as a message-oriented connected socket where you take an object and say, stick it into this connection, and it'll pop out the other end as that object. So it's essentially, it's still built on sockets. It's just dealing with the send and receive logic for us, so we don't have to do it. And we've actually seen that in action when using a pipe. In a pipe, you can stick stuff in at one end, it pops out the other end very transparently. So here are the methods of connection objects. Will look very similar. It'll look like a pipe. Send, you pass an object in. And notice that the only restriction here is the object must be pickable. There are also some other restrictions on size. For example, if you have a 32 meg plus object, very large object, you might get a value error exception. It will say that the object you're trying to pickle is too large. But for the most part, you could take an object, send it through to the other end, and on the other end it'll just receive that object on the other end. So the receive, that will then block until there's something to receive, and an object will pop out when it does, and this will have the return value of this will be the object that was sent. So for example, if I were to say send and then put quote hello, that would send a string hello, and on the other end, when this would return, I would receive that string hello. Or if on this end I would to send some sort of object like a bullet list on the other end, the receive of this, the bullet list will pop out the other end. And when we're done, we can close the connection. There's one other method here that I think is useful to mention, and that's you can do poll and have a timeout, and that will return whether there's any data available to read. If the timeout isn't specified, that'll return immediately. And if timeout is provided, that has a number of seconds. So you can say, hey, poll, wait for 1 second, and then tell me whether or not there's any data there that's available to be read or not. So this can be used to make it so your program doesn't necessarily block on a receive. You could say pull it, pull it, pull it. Oh, now there's something there. Let's call receive. All right, a couple final object methods for that. The file number is the file descriptor or handle used by the connection. Probably never going to need to deal with that. But then it also has this message send bytes and receive bytes, which allows you to use that connection object like you would with a normal socket. Allows us to send a number of bytes, and on the receiving end, receive a number of bytes. There's also this one that's receive bytes into, which allows you to read bytes into some existing buffer array at some particular position. So you could read data in chunks into some sort of buffer if you wanted to, rather than having this return a single object at some position. Okay, now, just like with sockets, there need to be two ends of that connection, a listener and a client. So the listener is the equivalent of the socket server. The client is the equivalent of, well, the client. So let's look at some example code. This will make a lot more sense, I think, if we look at a little bit of example code here. So here's some example code. Here's the listener at the top. Notice that we specify the address just like we do with sockets, and we do multiprocessing.connection.listener object. We put in the address, which has those two parts. And then notice it has this auth key, which in this case is a byte string of secret. This auth key can be useful because one of the problems you might think with a distributed system is, what if somebody who's unauthorized tries to connect to my service and tries to screw it up, or they try to get data from it when they're not authorized to? Well, there's this optional parameter auth key that you can specify that says they have to have the right key in order to connect to this. And notice we don't have to handle that. The multiprocessing.connection class handles all that for us. So here, all we have to do, notice we don't have to bind, we don't have to listen, we don't have to do any of that stuff. We just say, hey, make a listener class or object with this address and that as the authentication key. And now we enter this while loop just like we did before with sockets, and we say listener.accept. Once we've accepted, we can do list connect or that connection.receive. And once we're done, we do connection.close. Now, you might say, well, this looks an awful lot like the code for sockets. What's the advantage? Well, one of the advantages is, notice we didn't have to have those extra function calls here with bind and listen. The other advantage, when we do a receive, we're guaranteed that what this returns, if it returns data to us, was the object that was actually sent. And this comes in as an object, not just a byte string. So in this case, I did an example where I'm passing in this dictionary called player data that has the player's name, their X position, their Y position, their health, their speed, and their angle. And I'm going to pass that entire object in. And notice how easy that is to do with this connection object. So multiprocessing.connection.client. We pass the address of this same server along with the port number to it. We provide the same secret authentication key. That allows the connection to then be created. And once the connection's created, we're sending this player data. So connection.send player data. Notice I'm sending that dictionary object. I don't have to encode that. I don't have to use dumps to send it. I don't have to use loads on this end. That's all handled for us inside of the connection object. So on this end, I just receive that player data, and now I have that dictionary popped out over here. So I fed a dictionary in, a dictionary popped out on the other end, and we can now print that and we can see it. Once we're done, again, we close the connection on the client because we've already shared our data. Now, you can leave those connections open for a long time. You could open the connection. You don't have to open it, send data, and close it. You could open it, send data, receive some data, send data, receive some data. So you could have your let's say a multiplayer game, open that connection and leave it open while the game is being played. And when the game is done and you exit the program, then you close it. Okay, so here's what the output to those would look like. It's waiting for a connection. Connection was accepted. Here's the player data I received that was sent from the client. And then it goes back to waiting for the next connection. And on the client, we connect, we send the player data, we close the connection, and we're done. But the cool thing about this, notice here's that dictionary that popped out that was sent from down here. And this will work, like I said, on the same machine or the same LAN or cluster or across the internet. So this is a way to have a process communicate with another process that's somewhere else on the internet or maybe even on the same machine as well. Okay, so a couple notes here. Note that the connection objects with using listeners and clients greatly simplifies the exchange of data between two processes as compared with socket. It doesn't seem that much different. The main advantage is that we can feed objects in, instances in, have those pop out the other end. And since almost everything in Python is an object of some sort, it allows you to share data from one process to another one very easily. One thing to note, though, is that the objects have to be pickable to be sent using send and receives. Objects that aren't pickable have to be converted into some sort of buffer of something that is pickable before being transferred. And you might say, well, what is pickable and what is not, and how do I know? Well, generally, things that are built into Python, dictionaries, lists, even object instances, those are pickable unless parts of them are not pure Python. So for example, an example of that would be like the display surface in Pygame, if you've used Pygame to do graphics. That's really implemented behind the scenes in a library called SDL, and it's not really just Python code, so it can't pickle that. So if you try to sum something that's not pickable, you'll get an exception that gets thrown. Now, while connections are doing the serialization, deserialization for us, there may still be advantages to doing it yourself using one of those other methods like JSON and message pack. The main advantage I can see for message pack is that it is more compact and uses space more efficiently and runs faster. And an advantage for JSON is that it's more universally used than Pickle. In other words, it's cross-language. And if you do want to use one of those other interfaces, you just use the send buffer and receive buffer. You can still use the connection object. Okay, to finish up here, I did want to mention those other options just briefly here. That there are other distributed computing interprocess communication methodologies that are available. And most of them are implemented as some sort of library or framework that you can use. Some of them, like I've listed here, MPI, Pyro, Ray, a lot of other ones. And where Pyro and Ray are kind of Python specific, MPI is a standard that allows communication with other distributed systems and that are maybe even implemented in other languages. And then Pyro makes accessing remote functions and methods, method calls really seamless. In other words, you can just say, hey, here's this object I want to access the methods of. It's on another server somewhere, and then access them. So if you want to think about like the ornamental garden problem that's distributed, you have a computer at the entry gate, one at the receive gate, and they both call methods on some distributed object that's in a server somewhere. Then they could just say, whatever that distributed server is, it's a Pyro object, so set it up via connected to that, and then you treat it just like you would a local object to do like enter and exit or whatever you want with it. And Ray offers a range of distributed options, and I'll let you take a look at that if you want to. All right, so that's it for today. I got us in through a lot relatively quickly. I would suggest, strongly suggest, that you play around with some of that source code and try to get things to communicate now, because going forward we're going to have other labs coming up, and you're going to need to understand that stuff. And if you are in the networking class, we're going to spend a lot more detail looking at sockets and how they work, including how you program them in other programming languages. So look for that as well. That'll help your understanding of this. And if you already took the networking class, well, then you probably should, assuming you retained that information, at least you've been exposed to how sockets work at a lower level. And what I would suggest, if you don't really care about using sockets and how they work at a lower level, and all you want is to communicate between processes, I would suggest you use the multiprocessing.connection, since it's a little bit easier, a little more abstracted. Or I'd strongly suggest looking at one of these other methodologies that's down here. All right, so that's it for today. Everybody stay safe, and I'll see you next class. And we're going to kind of continue adding a few more things, and then we've got another lab coming up as well, so look for that. That's it for today. Everybody get out and enjoy the spring weather. It's starting to be nicer out. Pretty soon the trees will start blooming. But that's all for today, and I'll see you guys next time.